Alright, the next question we can look at is uh, the RVHS paper. So this is for alkenes. So we'll look at it. The hydration of alkenes that can be carried out by reacting alkenes with borane, which is BH3, with treatment with alkaline H2O2. The product is an alcohol. State the type of stereoisomerism and draw the structure of each isomer. So figure 3.1, you can clearly see there's a chiral carbon right here that is attached to four different groups. Okay, and this will cause the and you know that a pair of enantiomers they have a non-superimposable mirror images of each other and have no plane of symmetry, no center of symmetry, and so forth. So if you look at the answer below, okay, the answer is not below. The answer is here. So just make sure you have the mirror and then draw all of it accordingly in the tetrahedral geometry. Next question is define an electrophile. Uh, for this case, we have to make reference to BH3. So BH3 is actually a Lewis acid that is an electron pair acceptor. So if you remember the definition of electrophiles, okay, that's good, but not only that, you must also specify. So this is your definition of electrophiles that is usually in the textbooks, but you also have to indicate that BH3 is a Lewis acid, no octet of electrons, and have an energetically accessible vacant orbital to accept the pair of electrons. Okay, then next part is the mechanism. So in this case, don't worry, electron rich goes to electron poor. So boron is less electronegative than hydrogen. So given it's less electronegative than hydrogen, we will be able to assign our partial positive and partial negative charges. The partial positive is here. Okay, let me use a lighter color. Partial positive here and partial negative here. And our nucleophile is the alkene bond, so the alkene group, and we will make the alkene group go attack the electrophilic boron, and the bond pair of the BH bond will come down to attack the carbon right here. Okay, and this forms the transition state. Okay, all good. Now predict the major product of the following reaction. So we can use the information above. We see how the BH3 group. Uh, in this case, it's quite a special case. The BH3 group it goes against the Markovnikov rule. It goes to the less substituted carbon right here, and then followed by H2O2 and in alkaline medium, it causes BH2 to be converted into a OH group. So in this case, predict the major product. We will ensure that the OH goes to the less substituted carbon. Okay, so next part, which I believe should be the last part. Alkenes undergo a electrophilic addition with halogens in an exothermic reaction. So exothermic reaction, that means my enthalpy change of the reaction should be negative. Draw a labeled energy profile diagram between the reaction, for the reaction between ethene and liquid bromine. So first off, uh, other than enthalpy change of reaction we need to label, we also have to label the activation energy. So note that since it's a two-step reaction, I must have two curves and two activation energy, with the very first activation energy being much higher than the second one because the first step is a slow step. So I'll show you the answer below. See that the activation energy of the first step is much higher than the second step because the first step is the slow rate determining step. Okay? And you label your enthalpy change, which is a negative sign, and make sure you label the reactants carefully. Alright. One more thing that I would like to show you is that notice how it might seem weird when questions go against what you have known, but this is the reality that you have to deal with in A level where they give you a new context. So one interesting thing I would like to show you about this BH3 that attaches to the less substituted carbon is that notice that it's to you it might seem like an anomaly, but actually it still obeys the same principles that we have all been always talking about. The fact that a tertiary carbocation must be formed. Okay, so I show you the B is actually partial positive, partial negative. Then if we assign these two carbons, this one will be partial negative and this one will be partially positive. So that you can see in doing so, we have a certain kind of attraction. If I do the other way round, okay, if I do the other way round, then I have a lot of repulsion. And these two bonds can't be formed, will not be able to form. Okay, so in this case, what I will do is assign the partially positive and partially negative in this manner. Okay, so notice that the partially positive is on the carbon that is more substituted, and uh this carbon right here is less electron deficient due to the three alkyl groups that are electron donating and increasing the electron density on this partially positive carbon right here. So this is less electron deficient and thus more stable. Okay, so this is it for the alkene question.